Hello and welcome to the PIC32 Architecture Overview webinar. My name is Nilesh Rajbharti. I'm responsible for managing the 32-bit microcontroller applications engineering department in Microchip Technology. I joined Microchip in year 2000 and I have had opportunity to work with PIC18, PIC24 and most recently the 32-bit PIC microcontroller PIC32. In about 15 minutes, I will provide a quick overview of the PIC32 architecture and some of its key features. I will not focus on specific PIC32 devices, but instead provide you with architectural details that are common to all PIC32 devices. At the end of the presentation, I will provide you with references from which you can learn more specific about the device of your choice. Let's begin. As for the exact agenda, I will show you several block diagram views of the PIC32 architecture and discuss major features in somewhat more detail. Finally, I will provide you with some pointers to help you get more information. With that, let's begin with the high-level block diagram of the PIC32. This is a simplified view of the PIC32 chip. The PIC32 employs the M4K 32-bit core from MIPS Technologies. The M4K is a Howard architecture-based core. It contains separate instruction and data buses connected to the bus matrix. I will provide you with more information about M4K in the next slide. The core connects to the rest of the modules via bus matrix. The bus matrix is a high-speed switch. It establishes a point-to-point connection between modules. Modules such as the CPU core, USB and DMA connect to the SRAM, SPI, UART, etc. via the bus matrix and peripheral bus. The bus matrix runs at the same speed as the CPU, while the peripheral bus can be programmed to run at a different clock from the CPU. The exact bus clock is determined by the peripheral bridge setting. In this block diagram, notice that the PIC32 uses a 128-bit wide flash memory. Such a wide memory path is specifically designed to increase the instruction throughput and improve overall CPU performance. To further enhance the performance, the PIC32 employs a 128-bit prefetch cache module. This module can be programmed to look ahead and prefetch the next 128 bits of instructions and store them in an on-chip cache memory. This module is the reason why the PIC32 can continue to provide high performance even when the CPU is running faster than flash memory speed. Now let's review the block diagram one section at a time. We will begin with the core. Here is the inside of the M4K core. The M4K core uses a 5-stage execution pipeline. This means that each instruction is executed in 5 different stages. Once the pipeline is full, the M4K core executes one instruction per CPU clock. The MIPS Technologies rates its M4K core at 1.5 drystone MIPS per megahertz. As a microcontroller user, you should be more interested in knowing the drystone performance of the entire chip, that is, core and the microcontroller memory system put together. We at Microchip Technology have conducted our own drystone tests of the PIC32 and they confirm that the PIC32 also offers 1.5 drystone MIPS per megahertz at zero wait state flash operation. As with any other microcontrollers with slow flash memory, when running at faster than flash speed, drystone rating would drop. However, in the PIC32 case, the on-chip prefetch cache and high-speed SRAM minimizes that performance drop. When it comes to memory mapping method, the PIC32 uses the unified memory map, meaning that both instruction and data space reside in one linear address space, each occupying a unique range of addresses. With this scheme, you as a programmer will use one address pointer to access both instruction and data memory areas. Another point to note is that the PIC32 core can execute from RAM. Typical Howard architectures do not allow execution from RAM, but the PIC32 includes a special bus matrix configuration that allows it to make part of the RAM executable. The PIC32 uses the high-performance version of the multiply and divide hardware module. A very powerful feature of this module is that it contains its own autonomous pipeline. As a result, once the CPU issues a multiply or divide instruction, the CPU may continue to fetch and execute next instructions while the multiply and divide unit performs calculations in parallel. If the CPU tries to access the result before the multiply or divide operation is complete, the CPU will stall until the operation is complete. There are different cycle counts for multiply and divide operations. It takes one cycle to perform 16 by 16 or 32 by 16 multiply operation and 2 cycles for other sizes. The divide operation takes from 11 to 32 cycles. Exact cycle count depends on the dividend operand size. Smaller the dividend operand, shorter the divide operation. By default, the PIC32 executes 32-bit instructions. The 32-bit instructions are designed to provide higher performance. If the application is code size sensitive, it may use MIPS16E instructions. The MIPS16E instructions are 16-bit wide. With the use of MIPS16E instructions, application can save up to 40% of code size compared to the 32-bit instructions. There will be a reduction in performance when using MIPS16E instructions. However, with the 128-bit wide prefetch cache, some applications may see no adverse impact. The PIC32 architecture uses a concept called busmaster modules. The busmasters are a special set of modules that can initiate a read or write transactions of other modules called targets. For example, the CPU can read and write to SRAM or any other peripheral. Similarly, the DMA can read and write any other peripherals on the bus. At present, CPU, ICD, USB, and DMA are the busmasters in PIC32 architecture. Future PIC32 products may add more busmaster modules. The busmaster modules run at the same speed as the CPU. All busmasters except the CPU essentially have an integrated DMA capability to autonomously perform read and write of a peripheral. They can transfer data within the microcontroller or outside of the microcontroller without any assistance from the CPU. The busmasters may read and write other busmasters too. For example, the DMA module may read or write USB registers. However, the busmaster cannot access code registers in the CPU. Only the CPU can access the code CPU registers. Peripherals such